Okay, good afternoon. My name is Joe Circello. I'm from NXP Semiconductors, and I'm here today to present some data on what we term software PPA metrics. So the concept of power, performance, and area is fairly well established in SoC design in terms of optimization points. But what we would like to do in this work is redefine this into a more software-oriented context, specifically for microcontroller applications. So in this context, P, the first one stands for power in terms of memory accesses, both instruction fetches as well as data load and store access rates. The second P has to do with relative performance in terms of execution cycles and also dynamic instruction path length. And then finally, the A stands for relative static code size. So I guess you could say this is yet another presentation on code size. The work that we are going to be presenting today is further limited to specifically talking about relative static code size because of time constraints. And oftentimes in constrained MPU compute environments, this is a very key factor in the overall SoC design. And that's because typically non-volatile or ROM storage areas tend to be relatively large components on the device, and they also consume a relatively high portion of the active power. So optimizing for minimization of those hardware components is a very key parameter in the overall SoC design. So this work in particular, we do a lot of what I would term subsystem-based SoC design, where oftentimes we have subsystems that have processing elements in them, and these appear as black box devices within the overall chip. And in particular, what we've done for this work is look at two production security software releases. One is from our IMX family of application processors, and the second is from a crypto library that's used in a number of MCU devices. So the original implementation for these security subsystems were based on ARM Cortex-M cores. And what we are doing here is really retargeting to look at the RISC-V ISA, specifically the RV32 IMC configuration, and then trying to look at the relative code size across different compiler optimization levels and comparing between ARM Cortex and RISC-V. If we go into a little more detail on the software packages, the first package is from the IMX family, as I mentioned. It's about 100K lines of source C code, and the comparison for this particular software package is looking at GCC for ARM Cortex-M4 versus the RISC-V GCC compiler. For both packages, we're comparing measured code size of the text and read-only data sections from the package. And then we are also looking at various compiler optimizations, in particular looking at OS, O2, O3, and then for the RISC-V targets, we are also either including or excluding the msave restore flag, which has to do with optimization at function, prologue, and epilogue things. And you can see the specific revisions of the compilers that we used on the chart there. The second software package is this crypto library that we have, and this is about 40K lines of source C code. And for here, we actually did two separate comparisons. We again did Cortex-M4 GCC versus RISC-V GCC, and then in addition to that, we looked at ARM compiler for Cortex-M4 versus the RISC-V GCC. And again, the specific revisions are there. So these are the results from the first software package. This was the production security package from the IMX family. And you can see that there's two representations of the data here, a chart on the left side of the diagram, and then a tabular form on the right side. On the tabular form, you can see the individual columns have the specific size, static code size in bytes of this particular image. Starting with the Cortex-M4 followed by the RISC-V target. And then the highlighted column there shows the relative size difference between RISC-V versus the Cortex-M4. And as you can see on this particular topic, or this particular package, we had a range of about 1.08 to 1.15x growth static code size growth for RISC-V versus the Cortex-M4. And we thought that that was relatively within the range of expectations that we were starting off with. The final two columns on this particular chart show the size of the static code size for the different compilers using the OS as the baseline, and then just looking at how much growth we had in the object file as we went to 02 and 03 optimization levels. And you can also see the improvement in size that the MSave restore option provides. This is the second software package results. Again, same format. Here, though, we have an added compiler in the mix. So the first column, data column on the table shows the Cortex-M4 sizes. That's followed by the ARM CC code sizes, and then the column next to that is the RISC-V sizes. And then we've got the two highlighted columns that are showing relative code size, GCC to GCC, which is the one on the left, and then on the right it's the ARM CC versus GCC for the RISC-V. So here the code size growth was considerably larger than we thought, or we expected, I should say. I should mention also that the ARM compiler, we use the O-space optimization on it and an execute-only flag. And what we're seeing here is considerably outside of the range of what we expected in terms of static code size. So looking across both compilers, you see a range from 1.29 to 1.52, which is fairly large. So this was a bit of a surprise to us. I should also mention that on this particular software package, we also looked at the size for RV32IM, so not including the compressed instructions. And what we measured there was the addition of the compressed instructions reduced the size of the RISC-V object by about 23%, which is well within kind of the expectations that have been already published. So that seemed to be okay, but when we looked across the entire thing, quite a sizable and unexpected difference. So just some additional observations about this software package number 2. We were, obviously the data led us to try and look into more details about exactly what was going on here. And there were a number of attributes that were appropriate and applicable to this particular software package. First of all, this code is very highly modular, a lot of relatively short functions. There's a lot of indirect memory pointer references within data structures. The APIs have a large number of parameters associated with them. And there's a relatively high memory, data memory, loads and store reference rate per instruction. The other thing that I should mention, and we're still trying to understand the potential implications of this, but because this was a security library, it made use of an internal secure coding guideline standard, and we're really trying to understand what exactly, if any, that particular coding style had on these results. When we look at a side-by-side comparison of compiler outputs, there's an awful lot of commonality in terms of basically one-to-one correspondence between instructions coming out of this, in this case it's GCC, coming out of the Cortex-M4 GCC output versus the RISC-V GCC, other than specific things related to function prologue and epilogue. There's definitely a difference there. So we think that there's certainly the need for us to do further analysis on here to try and get a better understanding of exactly what's contributing to this large delta. But at this point in time, this is the data that we've measured and wanted to present today. In terms of next steps, we're going to continue this static code analysis, looking at several other production application areas that we have that we're interested in, as well as we have to go back, and this just covered the A part of the PPA, so we want to go back and look at the power and performance, redefine power and performance metrics for that also. So we think that will provide some interesting information about access rates, also things like the stack memory footprint and how that's going to go on. And finally, I would just like to acknowledge Antoine and Pim who helped do a lot of the heavy lifting on the data collection. So thank you very much.